So this is example number 2 on linear elastic fracture mechanics. Let's consider this case. Um, this particular case, we have a plate that has a width of 1.5 meters, a length of 2.8 meters. So let's make some drawings here. The case that we are working here has a through the edge crack. So through the edge crack is this case from figure 5.26. So the dimensions that we have in the problem are the following. This is A, and note one difference from the previous example. The B, this is B is not 2 times B, and this is A is not 2 times A. You have to be very careful, and you have to always look at the figure and be very careful in how you choose your A and B's. Okay? In this problem, it says I have a thickness of 30 millimeters, and I should convert that to meters for consistency's sake. You have a total height 2 times h of 2.8 meters. You have a width b, this is your b, is 1.4 meters. You have a p equal to 4,000 kilonewtons. The whole idea here is it supports a tensile load of 4 meganewtons. And throughout the inspections, we want to make sure that we can have a crack, but no larger than 2. We don't want a crack larger than 2.7. So the question is, given two alloys from table 5.1, they're considering this application, which one should we use? Now he's saying to use a safety factor of 1.3. And also is saying minimum weight is required. So when I do the problem, first of all, this 1.3 safety factor you're saying is the same as your design factor. Okay, so your design factor will be 1.3. So immediately know from the problem that your P required in this problem would be ND times P, and that would be 1.3 times 4,000, and that would give you 5,200 kilonewtons. Okay, in the problem, we know that it stated that your maximum A has to be 2.7 millimeters or 0.0027 meters. It's important, this conversion. You always have to work in the correct units. Okay. Couple of things that we can do before we move on is we can come to the table, to the chart. You can go to this chart and let's go and find our beta. We're going to need it anyway. So realize that A over B is equal to 0.0027 divided by 1.4. And this is basically very close to 0. And this value, note that it doesn't start in 1, it starts on top of that. This is the value of 1.5. So approximately, I would say that this is 1.1. Beta is equal to 1.1 in our problem. Okay. So now we will move on. Oh yeah, it's 0, right? A over B, and you are basically at 0, and all the curves actually end up in the same spot. Otherwise, you can also say you have H over B. H was, in your problem, H was 2.8 times 2. This was 1.4. This gave you equal to 4. So you're really working with a very, very large, I'm sorry. This is actually equal to 2. So you may be working with probably this curve right here. That's the one that you should be using. But that curve anyways, I'm working at 0, so I'm located right there. This is 1.4, by the way. Okay, so the problem is saying, go to the table 5.1 and choose these two different titanium materials, okay? From these two titanium materials, choose the one that actually will make it safe and to give and minimum weight is required. Now, the minimum weight requirement, what he's saying is, I want to make sure if I want minimum weight, right? So weight is equal to mass times gravity. Gravity cannot be changed. So it's the density um, times volume times g. Then density, this volume is 2 times h, b times t times g. If we assume that both titaniums have about the same value for my density, okay? If I say this is approximately same because titanium is the same titanium material, so we say that rho is almost equal to rho 2, so it's basically the same. So this is the same. This is given in the problem. This is given in the problem. This is known that's supposed to be working in the same application for the same G. The only thing that's left is to choose T. So the problem is saying really find the minimum T that will satisfy this problem, okay, that will make the problem safe. So before we start the problem, before we do anything, the very first thing we want to do is we want to use the materials. We got two different materials, okay, and both are the same material but have different properties. The first one, it says this is 115 megapascal square root of meters. Second one is sigma yield is 910 megapascals. So if I just go ahead and evaluate where my transition length is, 1 over pi is equal to KIC divided by sigma yield. If I replace the values, I find this gives me 0.083 millimeters. In the second case, second material, and again go to this table and you can see this is the first material. This is my first material. This is a critical fracture toughness for mode 1, and this is sigma yield for mode 1. So they are not one under the other. I just have to look under my to my right hand side to get these values. Okay, so this value is 55 megapascals square root over m. Sigma yield will be 1035 megapascals. Your transition length will be 1 over pi KIC sigma yield squared, and that will give you a value of 0.90 millimeters. Now, note that in the problem, I have a crack of 2.7 millimeters. So immediately when you know this is 2.7, in this particular case, my A, so if I divide this into parts, in this segment right here, my A is actually bound by 0 and AT. So I know this is going to be more critical, my yield criteria. Most likely it's going to yield first. We're going to check it. We're going to show that it's actually indeed is going to yield. In this particular case, I can show that my A is actually bigger than AT, so therefore fracture is going to be more critical. Okay, and we will show this as we go. So I can save myself time and just check for yield. Here I can just check for fracture and that will be good enough. However, just for completeness, and to explain how these problems are done, let's go ahead and evaluate yield for both cases and fracture for both cases, and come back to this. Okay, so if I'm working for the yield criteria, the yielding criteria, what says your factor of safety has to equal to sigma yield divided by sigma required. Okay, and that has to be bigger or equal than 1. So from here, sigma yield has to be bigger or equal than sigma required. And sigma required is nothing else than, so let's continue here. Sigma yield is bigger or equal than P required divided by T. Remember, you have to use the true distance in your problem, the available distance here. Okay, so is this we are working with this segment right here. This has broken. This is the only thing that's left. This problem from your textbook, and I believe there's a mistake in your textbook, how your textbooks does it. You should have actually been B minus A, and your book doesn't use that. So let's continue. Then your problem, you can solve for thickness by doing little algebra here. P required is divided by sigma yield B minus A. Okay, so now we have two materials. For the first material, your sigma is bigger than 5.2. This is your load is given. The first case, your sigma yield was 110 10 to the 6, and that comes from here. I'm using this as my case 1. You can see 910, and that's divided by 1.4 minus 0.0027, and that gives you a thickness of 4.09. So minimum thickness of 4.09 millimeters. In the second case, your T has to be bigger or equal than 5.2 times 10 to the 6, divided by 1035 times 10 to the 6, also divided by 1.4 minus 0.0027. If you do the math, that gives you T is bigger, has to be bigger or equal than 3.6 millimeters. Okay, this is all I did for yield. Now let's do the second part of the problem, which is fracture. And according to our analysis, we know that yield was most important on this side. But just for completeness, not here, but just for completeness, let's just do fracture for both cases, and it actually works as a good review and exercise. So now I have fracture, initiation of fracture. Initiation of fracture. We know that your factor of safety has to equal to your critical fracture toughness divided by your fracture toughness. So bigger or equal than 1, or I can rewrite this as a critical fracture toughness bigger or equal than mode 1 fracture toughness. And then I can go ahead and further simplify this. This is KIC, not simplify, substitute this value. This is beta sigma pi A. Just recall this is sigma no crack. Okay. So now I can go ahead and replace all the values there. and I can see that in your problem, KIC has to be bigger or equal than beta, P required divided by thickness times B, and pi times A. Okay, now I can resolve for T from here. So your T has to be bigger or equal than beta P required divided by my first, the fracture toughness for mode 1, and I take the square root of A. Okay, so let's do both cases. The first case is the first material. For the first material, we know that beta is equal to 1.1. We found that at the beginning of the problem. This is 1.1, that's given. Then your P required, we also found that beginning of the problem is 5.2. So this is, um, just give me a minute. Okay, so this will be 5.2 times 10 to the 6 has to be divided. Oh, there's a B missing here. I'm sorry. This B right here. So Ki will be 115 times 10 to the 6. This value is B. B will be 1.4. And this is square root of pi. And please note that I have to put this in meters. Okay, there has to be conversion, otherwise you're going to get an error. So if you do this, you find the thickness is actually equal to 3.27 millimeters. This is the minimum. If you do the second material, that basically everything is the same. The only thing that's going to change is the value of the material itself. This material is different now. This material is 55, 10 to the 6. This is second material. Everything else is identically the same. Square root of pi 0.0027. If I do this calculation, I find this gives me 6.84. Okay? So let's put everything in a tabular form to see how everything, to understand how the numbers work. So let's do material A. I found for material A, I found that my minimum thickness was 4.09 millimeters. For my initiation of fracture was 2.29 millimeters. And the maximum thickness here that I would use for your design, for your selection, was you always choose this maximum from these two. Okay? So if you want to be safe on both cases, if I choose this, it's not safe here. So, but anyways, I know that this was going to be yield, driven by yield, and the reason behind I know that because A was smaller than AT, and it was bigger than 0. I knew that. So I could have just started the problem, done the yield, and stopped the problem right there without having to go extra calculations. In the second material, this was 3.60 millimeters. And this gave me 6.84 millimeters. And the answer, then the maximum value is 8.84 millimeters. And we kind of knew that your fracture was going to be more critical because your A was bigger or equal than your transition crack length. So that's why it's important to always calculate your transition crack length to decide which of the two cases we are doing. It simplifies your analysis greatly because you're working here, you know this was fracture, initiation of fracture. That's why you found that this was the answer here. You know this was going to fail it was most likely going to fail because of yielding. That's why we choose this. And that's the answer, right? You can see it down here. So from the both cases, which material do I choose? Remember the way we started the problem, the whole idea is I want to choose a value so it has the minimum thickness, because minimum thickness would give me minimum weight, right? So from the both cases, as you can see, this material A seems to be the most promising material to meet both criterias and yet to show that it's safe. So the solution of your problem should be I should select the material. The material selection should be the following. The material selection should be use the value of tie 6Al 4V that has a mode 1 fracture toughness of 115 megapascals square root of m and a yield strength of tensile yield strength 55 megapascals. Okay. And what's interesting in this particular problem, just note this, that in this problem, okay, for this particular material, this stronger KSI, you see this had a stronger KSI than this, requires larger T than yield, right? This had a larger KSI. So I did this opposite, so it's saying a weaker. A weaker KSI is going to require a larger T than in yield. A stronger KSI is going to require a smaller T than yield. And you can see from the problem itself. But the solution to the problem that we are looking for is this one right here. This is the material that you will use. And for this particular material, you have a thickness of 4.09 millimeters. Okay, this is the solution. This is a completion of example number 2.